salt hydrolysis. And we found out that that region is 8.72. So I'm going to put the 8.72 over here. That is our equivalence point pH. So that is our skill number 1 and skill number 2. We are going to talk about skill number 3. And skill number 3 is buffer. Guys, buffer is the next most tedious, I would say. But buffer is nowhere as nearly as tedious as salt hydrolysis. Salt hydrolysis is always the most tedious. And because it is the most tedious, it will always be tested. Yeah, like it will guarantee be tested. Buffer, right? You must remember this. In order to form a buffer, you need a mixture. And that mixture must contain the conjugates. So for example, since our ethanoic acid is reacting with the NaOH, you can have a possible buffer situation. So again, I'm going to write the neutralization equation to give us a sense of direction, okay, of what is happening in the reaction. So the acid and the base are reacting to give us salt and water. And remember, right, in order to form a buffer, the weak acid over here must be in excess, and the strong base over here must be in limiting. Now, guys, remember this, okay? At the equivalence point, our acid and base are on a 1:1 ratio. They are equal, which means that anywhere before the neutralization point and after the neutralization point, they are not at equal amounts. And I want you guys to think, is it in the before region or the after region that the acid over here is in excess, that the weak acid is in excess? Now remember, the weak acid is waiting inside the conical flask. That NaOH is being added drop by drop. And at this point, they reach 1:1. So does that make sense that actually in this entire region, our acid is in the large excess? Because in this entire region, it is before they reach 1:1. And that means in the beaker here, in this region, our weak acid is in excess, which means this region is our buffer region. Okay. So that means what? That means if you are going to be asked to calculate the pH of any volume in this region, you are supposed to do it like it is a buffer. So let's say I want to calculate what the volume, what the pH is when the NaOH volume added is 20 cm3. Okay, guys, what you need to do all the time is to always figure out if I add 20 cm3, what is left in the beaker after the acid and the base have reacted. So I'm going to do that. I'm going to use ICE table. Okay. We know that ethanoic acid start with 0.0025 because we just calculated in the previous case. At 20 cm3, we are going to get 0.0020 moles of NaOH because this is the concentration line. Yeah. And you can see that they are not on a 1:1 ratio. And our NaOH is the limiting reagent. So he's going to react. So our change is going to be minus 0.0020. We are going to add 0.0020. No salt. We don't care about water. This is going to be 0.0005. No more NaOH. 0.002 of the salt is formed. Can you see this is a buffer scenario? You have the acid and the conjugate base left in the mixture. This is a buffer scenario. If it is a buffer scenario, all you need to use is the buffer equation. Okay, the Henderson-Hasselbalch equation, which is pH equals to pKa plus log the conjugate CH3CO2 minus divided by the weak acid concentration. All you need to do is to put in the different variables. pKa is negative log of the Ka value. Ka value is given, right? Plus log base concentration, which is 0.0020 divided by the total volume. At this case, the total volume is 25 plus 20. 0.0005, which is the moles of our acid divided by the total volume. Convert everything back to dm cubed, but if you're really sharp, you can see that I can cancel off all these terms because they are repeated on the numerator and denominator. You don't even need the volume, you just need the moles. When you calculate this pH, you will get 5.35. Just put inside the calculator and you just calculate accordingly. Yeah, so this will give you the pH at 20 cm3. Guys, you must remember that so long as we are in the buffer region, the only equation you use is the buffer equation. You should not be doing weak base calculation, weak acid calculation. You should not be doing salt hydrolysis. This is a buffer, so you use the buffer equation over here. Okay? Now, in the buffer region, there is one very easy spot, and that easy spot is the center of the neutralization. So, for example, 12.5. Now, you must remember that if we are at this point, in the solution, there is only ethanoic acid. If we are at this point, all of our ethanoic acid is converted to ethanoate already. At this point, all of them are ethanoic acid. At this point, all of them are ethanoate, which means at the center line, we are at 50% of converting all of the ethanoic acid into all of the ethanoate, which means at this center line, the amount of ethanoic acid and ethanoate are the same. Now, some of you will not follow, so I will show you using hard math, okay, hard numbers. Ethanoic acid is reacting with NaOH to give us our salt, CH3CO2 minus Na plus. Okay, and you have H2O. You have an ICE table because we want to know how much is left. There is 0.0025 of ethanoic acid at 12.5 cm3. Basically, you have 0.00125 of NaOH. Our NaOH is the limiting reagent. Subtract. Add to the salt. 0.00125 of the acid, 0.00125 of the salt. There is no more base left. Can you see the final moles of the two conjugate acid-base pair are the same? And if they are the same, this is a buffer. On top of that, this buffer is at MBC, maximum buffer capacity, because the ratio of the conjugate acid-base pair are the same. And at MBC, the pH is equal to the pKa. So all you need to do that is to put in negative log and slot in the Ka value into the formula and solve. That will give you 4.74. This is the pH at 12.5. It is super easy. Okay? But of course, you must remember the principles of how a buffer works. What is maximum buffer capacity?